Hello and welcome to the presentation on the simply typed Lambda calculus. This is for CS 360 in the summer quarter of 2017. This is a presentation with Walter Gottlieb, Sean Jamison, and Noah. To start off the presentation, we're just going to talk a little bit about Lambda calculus. So what is it? It's a formal mathematical logic, and it makes up a universal model of computation. So it seems pretty general because it is pretty general. It has a lot of things that it can accomplish, and it's built up of only three small things, but with those three small things, variables, abstractions, and applications, you can actually do an amazingly large amount of things. You can do pretty much anything that the modern computer is capable of doing because it has become that model of computation that everything is tested on. So we're going to launch right into it. Lambda calculus has three things, like I said before: variables, abstraction, and application. A variable is literally can be a symbol, and then there's not much else to it. So it can be, there's two types of variables. There's going to be bound and free, and we'll discuss those a little bit later once we get into abstraction and application, because they won't make sense without those first. Abstraction is going to be kind of the meat of building your functions. So here we have the function, and it's lambda variable body argument, just to show you how it works kind of. And then on the right side I have kind of a more mathematical, classical, what you're looking at. So you have the argument of why the function, instead of lambda in this case, is mapped onto the set where we have the variable and then the body of the rest of your function. Then you have application, which is going to be called lambda reduction, which actually has three subtypes: alpha, beta, and eta. And these processes will give you the ability to evaluate your lambda expressions. So we're going to start with beta reduction. Beta reduction is almost like just plugging in your argument. So if you have lambda var body and then the argument here, so your argument is going to take the place of anywhere where variable is, where var, since it's next to the lambda, is your bound variable. So be your bound variables, which will then be replaced by your free variable. Alpha conversion is used kind of for places of ambiguity when you have nested lambda expressions. So in this case we have lambda x, and then nested inside of that argument is lambda y, xy, and then the argument for one of them is y. This, if you immediately applied beta reduction, will give you lambda y, yy, which is not correct because the y in one of them and the x in the other one are now being confused because they use the same symbol but are not in actuality the same thing. So the simple thing for this, it's called alpha conversion, and all you're going to do is you're going to replace the bound variable with something that has its own and clearly own variable name. That way when it is beta reduced after, this confusion doesn't happen. And you can see at the bottom, after this you'll have lambda y1, lambda x, xx, and that's with application. And then since we have no variables as arguments, it has to stop there. But if you give arguments, then they can be taken to a further stop. And then the last one is eta reduction, and this one is actually very simple. So if you have a lambda expression with its bound variable and then a function and then the free variable, where this bound function has no uses of that free variable, you can substitute it for just the function. So this would be like if you had lambda x mapped to absolute value of x, where we don't use these functions or this variable within the functions, then you're basically just using the abstraction just to introduce the absolute value function, where it's not actually taking the argument of x, it's taking something else, you're just introducing it. So you can just substitute it and just put absolute value in there, and then if this was nested within another lambda expression, that's where your argument would come from, and it wouldn't be x, it'd be y, or it'd be y1, or whatever else you're going to use there. Here's a couple examples if you want to pause the video and try to cover up the side of the screen and then see how it works. It's pretty straightforward, and you can take a second to do that. And then after this, we'll be moving on to kind of how you can take these expressions and get into a whole nother level of what this expression language is capable of doing, and that's kind of through church encoding, because you can use this expressions to build up anything, including numbers and Boolean values, and then from there, since you can do that, you can use functions to evaluate them, and you'll have true and false, and then logical ands and ors, and then from there you can build onto all kinds of other things, and that will be further discussed in the next section, which is church encoding.
Next, we'll be talking about church encoding in type lambda calculus. Several primitive data types can be expressed using functions instead of primitives using lambda calculus. This is known as church encoding, named after Alonzo Church. We can use church encoding to express booleans, numbers, lists, and more. Church encoding in its purest form uses untyped lambda calculus, but we can apply it to a type setting. So first, we're going to start with church booleans. We can define true and false using these functions above here. True and false are functions that each take two arguments and returns one of them. True returns t, and false returns f. It would be convenient if true and false both share a single type. If we want true and false to have a common type, we need to assume that true and false's arguments have the same type. The same type can be arbitrary, since true and false do not interact with their arguments, other than returning one of them. So we get this definition of a church boolean, which we call cbool. And then we define true and false in terms of the cbool. So now, using church encoding, we have an implementation of the booleans. Now that we have a definition of true and false, we can create common boolean operations, such as not. We can also extend church numeral encoding to numbers. So here we have functions where each natural number n is a function that takes two arguments s and z. In these functions, s is applied to z n times, and through this application you get the number that you want. The z argument should be the same type as the domain of s, and s's return value should also have the same type. We can thus develop the previous system for numerals into a type, which we have with C natural. Adding these annotations, we can then apply C0, C1, C2, etc. onto our C natural, and then thus have a church encoding for numerals. We can also define a type successor function. A successor function will allow us to get a church numeral's subsequent number. From 5, we will be able to get 6. From 8, we will be able to get 9. We can define it using here. And church success will return the subsequent C natural. We can also do different terms of arithmetic. We could do church addition in two different ways. The first method has us using succession that we just previously defined in order to define addition. We can also define church addition more directly without using succession. Finally, we can make lists using church encoding. In untyped lambda calculus, church lists are implemented similarly to church numerals. Unary notation is a number system based off of a single digit, where 1 would equal to 1, 2 would equal to 2, 2, 3 would equal to 1, 1, 1, and 4 would be equal to 1, 1, 1, 1. A number in unary notation can be considered to be a list of elements. Based off this design, we can create a church encoding for lists as such. Implementing null lists is relatively simple, and so by implementing list construction and implementing a null list check. The applications of church encoding. Church encoding is mostly used to show that there are more creative ways that we could display primitive data types. So while it's not very practical, church encoding can be used to build entire languages simply in itself.
The simply typed Lambda calculus mini language. We can think of church encoding, which we have just discussed, as a toolbox that has all the tools we need to construct a full functional programming language. This example, which is taken from the CS550 final project, shows the use of church numerals in Haskell to construct all parts of a functional programming language. As you can see here, we have variables, expressions, types, and declarations. Many kinds of expressions. We have variable expressions, absolute expressions, if expressions, etc., etc. This allows us to construct any kind of program that we want in a functional language. That was an example of a mini language built in Haskell, which features the simply typed Lambda calculus. As a matter of fact, Haskell is built upon the Lambda calculus. Its logo is even a lambda. I thought that was clever. What we have done here with this example is add simple types to it from the simply typed Lambda calculus. This is in contrast to other functional languages, such as Scheme, which we have discussed, which is based on lists and processes instead of being based on Lambda calculus. They each work in different ways, but they are both functional languages, and they can both work and function in the same ways. The simply typed Lambda calculus mini language. We can think of church encoding, which we have just discussed, as a toolbox that has all the tools we need to construct a full functional programming language. This example, which is taken from the CS550 final project, shows the use of church numerals in Haskell to construct all parts of a functional programming language. As you can see here, we have variables, expressions, types, and declarations. Many kinds of expressions. We have variable expressions, absolute expressions, if expressions, etc., etc. This allows us to construct any kind of program that we want in a functional language. That was an example of a mini language built in Haskell, which features the simply typed Lambda calculus. As a matter of fact, Haskell is built upon the Lambda calculus. Its logo is even a lambda. I thought that was clever. What we have done here with this example is add simple types to it from the simply typed Lambda calculus. This is in contrast to other functional languages, such as Scheme, which we have discussed, which is based on lists and processes instead of being based on Lambda calculus. They each work in different ways, but they are both functional languages, and they can both work and function in the same ways.
Alright, to finish the presentation now, we're going to look at the STLCs and Haskell implementation in the version from the CS550 course that's downloaded and implemented. Going down this list, a lot of them are actually pretty much direct copies of your church encoding type. Looking at that, so you got your bools, and at the bottom, actually, the last couple are going to be your church numerals. So you got 0, and then suck E, and then that's going to continue, and that's all of those. And then the next couple are application and other things, which are going to be typified by these rules on the left side. And in English, these rules are that number 1, if X has type row in the context, we know that X has type row. 2. Term constants have the appropriate base types. 3. If in certain context with x having type rho, e has type tau, then in the same context without x, lambda x rho, e has type rho to tau. 4. If in a certain context E1 has type rho to tau and E2 has type rho, then E1, E2 has type rho. So that's kind of a lot to take in right there, but this should kind of explain the type checking for this, and then there's a coding example that'll be attached that can be run with the rest of the STLC implementation that was done ahead for the CS550 class.